Welcome back to another video on design of experiments and analysis of variance. The main problems we need to address through proper design of experiments are bias and variance. Bias is when the results of an experiment are systematically pushed in one direction, usually because something in the way we designed or conducted the experiment is influencing the outcome. To eliminate bias, we can include a control group for comparison. Use randomization to assign treatments, so we're not picking who gets what based on assumptions, and sometimes apply blinding, where participants and even experimenters don't know which treatment is being used, so their expectations don't affect the results. Variance, or sampling error, is the natural variability in data that can make results unclear or less reliable. To reduce this variability, we use replication, running the experiment multiple times so we get a more accurate average. Balanced designs, making sure each treatment has the same number of observations so no group is over or underrepresented, and blocking, where we group similar experimental units together, like using the same machine or operator within a group, to reduce noise from known sources of variation. All of these techniques work together to help us design better, fairer, and more informative experiments, which leads to more confident engineering decisions. We'll dive into each of these ideas next. A control group is a group of subjects in an experiment that does not receive the treatment being tested, but is otherwise kept under the same conditions as the group that does receive the treatment. The purpose of the control group is to act as a baseline, so we can compare and see if the treatment really made a difference. Let's go over a medical example about testing a new drug to better understand the importance of having a control group when designing an experiment. Let's say scientists are testing a new medication for reducing blood pressure. The treatment group gets the real drug, while the control group gets a placebo, a pill that looks and tastes exactly like the real drug but has no active ingredient. Both groups are treated the same way otherwise. They come to the clinic, talk to doctors, take pills at the same time, and follow the same routines. If, after several weeks, the treatment group shows significantly lower blood pressure compared to the placebo group, we can conclude the drug likely caused the improvement, not just the act of taking a pill or seeing a doctor, which might have a psychological or behavioral effect. This setup helps eliminate bias and allows researchers to measure the true effect of the drug. Without the control group, we wouldn't know if people improved because of the drug or because of other factors like diet, stress, or even just believing they were being treated. In the statistical design of experiments, randomization means assigning treatments to experimental units by chance, not by choice or pattern. This is important because it helps eliminate bias by spreading out any uncontrolled or unknown factors evenly across all treatment groups. But why does that matter? In real-world experiments, there are always some confounding variables, things that affect the outcome but aren't the treatment we're testing. If we're not careful, those variables can distort our results. Let's go over an example together. We want to test a new fertilizer in a greenhouse. But there is a catch. The greenhouse has better lighting on one side than the other, and you're growing the same kind of plants throughout. If you decide to apply the fertilizer only to the brighter half and keep the regular fertilizer on the dimmer side, you've now confounded two variables, fertilizer type and light level. If the plants grow better on the brighter side in the no randomization case, how do we know whether it was the fertilizer or the lighting that made the difference? To fix this, we should use randomization. Randomly assign which plants get the new fertilizer and which get the regular one, regardless of where they're located in the greenhouse. This way, the better lighting gets evenly distributed between both fertilizer groups, and the lighting effect is no longer biased toward one treatment. By breaking the link between the treatment, fertilizer type, and the confounding variable, light level, randomization helps us make a fair comparison and draw valid conclusions about what actually caused the differences in plant growth. If the plants grow better on the brighter side, no randomization case, how do you know whether it was the fertilizer or the lighting that made the difference? To fix this, you should use randomization. Randomly assign which plants get the new fertilizer and which get the regular one, regardless of where they're located in the greenhouse. This way, the better lighting gets evenly distributed between both fertilizer groups, and the lighting effect is no longer biased toward one treatment. By breaking the link between the treatment, fertilizer type, and the confounding variable, light level, Randomization helps us make a fair comparison and draw valid conclusions about what actually caused the differences in plant growth. In experiments, replication means applying each treatment to multiple subjects or repeating the experiment on larger groups. This is essential for reducing random variability and increasing the reliability of your results. When we only test a treatment on one person, that person's unique characteristics might cause them to respond differently than average, whether the treatment actually works or not. That's why having just one subject in a treatment or control group is risky. Our entire conclusion could be based on a fluke. For example, let's study a heat lamp on lizard activity. Let's say we're studying whether a special heat lamp increases the activity level of lizards. In scenario 1, we place one lizard under the heat lamp and leave one lizard without it. The heat lamp lizard moves around more. Can we conclude the lamp caused the increased activity? Not really. Maybe that lizard is just naturally more energetic, or maybe it got more sleep. In scenario 2, we test the heat lamp on 4 lizards and keep another 4 lizards as controls. Then we measure average activity levels across each group. If the heat lamp group consistently shows more movement, we're far more confident that the lamp is responsible. As you replicate the experiment with more subjects, you reduce the impact of random noise, like one plant that happened to grow really well or poorly by chance. This idea is backed by the central limit theorem, which says, as the sample size increases, the sampling distribution of the mean becomes more normal and less variable, even if the original data is skewed or noisy. In a balanced experimental design, each treatment group has the same number of observations or samples. This kind of design is not only simpler to analyze, but it also gives you stronger, more reliable results. Balanced designs are important because they maximize statistical power, which means we're more likely to detect a real effect if one exists, and make our tests more robust. They hold up better even if some assumptions, like equal variances, aren't perfectly met. Imagine we're testing whether a new vitamin supplement increases the speed at which lizards move. In an unbalanced design, we give the vitamin to 2 lizards and keep 6 lizards in a control group. The results could be skewed. If one of the 2 treated lizards happens to be unusually fast, it might look like the vitamin works, even if it doesn't. The small group size creates high variability and low confidence in your result. In a balanced design, we give the vitamin to 4 lizards and have 4 lizards as controls. Now, we have an equal basis for comparison, which leads to more stable averages and a more powerful test. We're better able to tell whether the vitamin is truly effective. Balanced designs help ensure that each treatment is fairly represented in the data. When groups are equal in size, our analysis becomes more statistically powerful, less sensitive to outliers, and more trustworthy overall. In experiments, blocking is a technique where we group experimental units that are similar into blocks before applying treatments. Each block contains units that share some common characteristic, like environment, time, equipment, or operator. The idea is to control for a source of variation that is not our main focus, but that could still affect the results. This type of variable is called a nuisance factor. By grouping similar units together, blocking, and randomly assigning treatments within each block, we can reduce noise in the data caused by variability in the nuisance factor, improve accuracy of the experiment, and focus more clearly on the treatment effects we care about. Blocking is like repeating the entire experiment multiple times, once in each block, but in a more efficient and structured way. Suppose we're conducting an experiment to test 3 different fertilizers on plant growth. You plant seeds in pots arranged in 4 rows along a sloped hill. But there's a challenge. First, one side of the hill is shaded by trees, so those pots get less sunlight than the others. Second, because it's a slope, water naturally drains downward, so the bottom rows retain more moisture than the top ones. These 2 conditions, shade and moisture differences, are nuisance factors. We're not testing them, but they can affect plant growth and introduce bias into our experiment. Step 1. We divide our 4 rows from top to bottom into blocks because each row has similar water conditions. Block 1 is the top row, driest. Block 2 is the row 2. Block 3 is the row 3, and block 4 is bottom row, wettest. Here, water level is a nuisance factor we can control, so we block it to remove its influence from our fertilizer comparison. Step 2. Within each row, block, we randomly assign the fertilizers across the left to right layout. Some pots in the shade will get fertilizer A, some B, some C. Same for the sunny side. Since we can't fully control the tree shading, we randomize to ensure that each fertilizer has equal exposure to both sunny and shaded spots across the experiment. By blocking what we can control, water level, and randomizing what we can't, sunlight, our experimental design reduces the effect of water variability on our results, ensures no fertilizer is unfairly favored or penalized by random sun exposure, and gives us more reliable, unbiased conclusions about which fertilizer is most effective. This is a textbook example of the principle. Block what you can, randomize what you can't. Thank you for watching another video on design of experiments and analysis of variance. See you in the next one.